Alright, let's look at some IB style review questions for this test on arithmetic and geometric sequences and series, compound interest, and exponential equations. So here's an exponential equation question. We can see that this is an example of exponential decay as the graph is getting smaller and smaller and smaller each time. And in part A it says write down the temperature after 5 minutes. So 5 minutes is this axis, so let's draw a line from 5 minutes up to the graph and then trace it over, and it seems that this occurs at a temperature of 85 degrees Celsius. Alright, it says after how many minutes is the temperature 50 degrees Celsius. So here's 50 degrees Celsius. Looks like that's going to occur, maybe at 20.5 or even 21 minutes, something like that. It's just a bit of an estimate, and IB, when you're reading graphs, does tend to give you a little bit of leeway of plus minus 1 square. Alright, then it tells us what the equation for this function is. It's written as y equals 100 times 5 to the power of negative 0.02x. Now you might be a little bit surprised at this moment that this is an exponential decay function when you consider that the base of this power is greater than 1. Because I had taught you previously that when the base of the power is greater than 1 in the curve y equals a to the power of x, that's a growth situation, because we keep multiplying by something that's bigger than 1. It should keep growing. And that decay occurred when we had your a value is in between 0 and 1 in the function a to the power of x. That means that we're multiplying by a fraction each time, and it's getting smaller and smaller. And what I had said is true. What's happening here is that what would normally be a growth function has flipped over, and due to this reflection, the negative value has changed the growth function into a decay function. This is actually a clever way of quickly flipping a growth curve into a decay curve, that you just stick a negative in front of the coefficient inside the exponent. So it is possible for an a value greater than 1 to actually be a decay function if the exponent is negative. Anyway, let's get back to the question at hand. The asymptote, I'm not quite there yet. Part C, it says to calculate the temperature after 80 minutes. So let's substitute the 80 into this formula. 5 to the power of negative 0.02 times 80. So let's see what we get. 100 times 5 to the power, times 5 to the power of negative 0.02 times 80. And we get 7.61 if we round to 3 significant figures. You can leave it with extra significant figures if you like, but no matter how many significant figures, you should include the units, degrees Celsius. And lastly, we need to write down the equation of the asymptote to the curve. An asymptote is a line that the function is getting closer and closer and closer to. We can see that our curve is gradually getting closer and closer to horizontal, and you should know that a regular curve will have an asymptote of y equals 0, whether it's growth or decay. The only time that your asymptote is not y equals 0 is if you have had some kind of thing added to your function. So let's suppose our function was 100 and then 5 to the negative 0.02x, and then it said plus 80. This plus 80 shifts everything, including the asymptote, upwards to 80. And so now your asymptote would become y equals 80. But in this question, we don't have a shift upwards by anything. We're simply shifting upwards by 0. We're not shifting at all. And so the equation of the asymptote would still be y equals 0. Here's another way you can do this problem. We know that in a decay curve, we're getting closer and closer to the asymptote as x gets very, very large. So why don't we just put in the last entry that we had, but change our 80 into something really big, like 8,000 or something. And let's see what happens when x is very far to the right. What has our curve basically become? It's basically become 0. So you'll get 1 point, because you need to write an equation of the asymptote, you'll get 1 point for writing y equals, and 1 point for the correct number of 0, the value that your graph is approaching as you get very big. Number 2, we have an arithmetic sequence. We can see that the first term is 124. To find the common difference, let's take the differences between each pair of terms. The second one minus the first one gives us -7. The third one minus the second one also gives us -7. And if you keep going one more pair, you'll still find that you get -7. Therefore, the common difference, d, equals -7. Part B, we need to calculate the sum of the first 50 terms of the sequence. Alright, well, we know that this is an arithmetic sum, okay, because we were given that as an arithmetic sequence, so let's substitute into the arithmetic sum formula. N over 2 times 2 times u1 plus n minus 1 times d. Let's put this into the calculator. 50 divided by 2 times, open brackets, 2 times 124 plus 49 times -7. And we get an answer of -2,375. And lastly, we need to find out what is the first term that is negative. Well, it tells us UK is the first term, so we want to find out what the value of k is. That is to say, how many terms does it take until we finally get to a value of the sequence that is negative. You can see the sequence is going down, down, down. Eventually it should reach a negative number. So let's write down an expression for our ukth term. We know that uk will equal u1 plus k minus 1 times d, and we want this to be less than 0. Where is it going to be negative for the first time? And so let's substitute. Our u1 was 124, so where is 124 going to be less than, 124 plus x minus 1 times -7, where will that finally be less than 0? So let's go to y equals and put in our function 124 plus x minus 1 times -7. And there's our function. Let's look at the table, and we'll see where does it finally hit a negative number. Let's scroll down a ways. And it looks like I hit a negative number right there. Alright, when I hit 19 was my first negative number. And so my table then, I'll just explain to the reader that I made my y1 equal to u1 plus x minus 1 times -7. And now I've got a table where at 18 I was still positive, but when I hit 19 I was at -2, and that means that your k value you were looking for is equal to 19. That's when we finally got to a negative number. So it's u sub 19 will be the first term that is negative, but it's looking only for the value of the subscript, meaning the 19th term. There we go. Question number 3. We got the first term in an arithmetic sequence is 7, so u1 equals 7. And the sixth term is 22. Now we know that we can write the sixth term as u1 plus 5d, right? So if the sixth term is 22 and u1 is 7, then it should be quite quick to solve for d. We'll just bring the 7 to the other side. 15 equals 5d, and therefore if we divide both sides by 5, you'll find that d is equal to 3. Part B, it wants you to find the 12th term. So because it's looking for a term, we use the u12. That's going to be u1, which is 7, plus 12 minus 1 times the common difference of 3. That equals 7 plus 11 times 3. That's 7 plus 33, and therefore the 12th term is 40. And lastly, they want the sum of the first 100 terms. So again, let's keep using the arithmetic sequence, or in this case, sum formula. Sum of the first 100 terms. Well, that means that 100 is equal to n. So 100 over 2, and then we've got 2 times the first term plus n minus 1 times the common difference. Let's put this into the calculator. So 100 divided by 2 times, open brackets, 2 times 7 plus 99 times 3, close brackets. And we get a sum of 15,550. Okay? So these are our three answers. D equals 3, U12 equals 40, and S100 equals 15,550. Number 4, here's a geometric sequence that starts with 16 and then goes to 8 and then A and then 2 and then B. We need to first write down the common ratio. A common ratio could be found by writing any term and dividing it by its previous term. So 8 over 16 equals 1/2, therefore R is equal to 1/2, or 0.5 if you prefer. Now let's write down the value of A. So if I'm multiplying by 1/2 in order to get the next one each time, or you could think of that as dividing by 2, clearly A is 4, and then we divide by 2 again, and then we divide by 2 again, and B is equal to 1. And then it tells us that the sum of the first n terms, remember we'll be using the geometric sum formula, is 31.9375. So Sn is 31.9375. Now we know that Sn can be rewritten in a geometric series as U1, which for us is 16, and then R to the power of x, or n minus 1, divided by 1/2 minus 1. And so we want to find out, where is this y1 expression going to be equal to 31.9375 as I examine my table? I'm going to use a table because I know that the number I'm looking for, the number of terms, must be an integer. So here we go. I'll write down first 16 times 0.5 to the power of x, exit the exponent, minus 1, close the parentheses, and divide by the denominator, which is 0.5, minus 1, close parentheses. And I'm going to look at a table to find out when is my table equal to 31.9375. And I can see that that occurs, well, okay, it's maybe a little tough to see because my calculator has rounded it. It rounds it to 31.938, but that's pretty close. So that must be the value. So I'll write down my two rows. I've got row 8 and row 9. In row 8, I was only at 31.875. In row 9, I was 31.938, and I know that that's really 9375. So clearly, the n value then is that ninth row, n equals 9. And we'll continue the last three questions in the final video of this review in a minute.